Hello everyone. My name is Tufik Mohammed Ailan, and I'm one of the authors of the paper toward formalizing the emergent behavior in software engineering systems. And today I will be discussing our contribution into this paper. So our agenda will be a quick background and related work, and then I will dive into the approach that we have chosen to define and formalize the emergent behavior. I will use the same scenario example that I have used in the paper, and then we will conclude our work. So the emergence phenomenon actually is not a new subject for the academic discussion. It has been a subject of academic discussion for a long time in different fields and disciplines such as natural sciences, biology, computer science, and so on. So one of the examples that are widely used to discuss this phenomenon is the murmuration of the flock of birds, the bees and ants build in hives and colonies, and so on. And this is also the case in computer science. The phenomenon is not something new. The emergent behavior discussion is not something new. Many references in the literature, different definitions from different perspectives were given in this regard, but most of them probably are going around this, the Aristotle saying the whole is greater than the sum of the parts, which we did not find convincing at at our research group here in the Systems and Software Engineering Institute, and we thought it's not, most of the definitions are not concrete enough or are not formal enough to adopt when we develop emergent systems or when we discuss the emergent behavior. It's not something that is straightforward and explicitly mentioning how to detect an emergent behavior, what is exactly an emergent behavior. And for this reason, this was the main purpose of the paper, is how to provide a more formal or more concrete definition to the emergent behavior. So our approach was simple. At the beginning, maybe we started with what is not an emergent behavior. We went back to the development process of software systems, and what we wanted to do is at each phase in the development process, we try to recognize what kind of behaviors, and then we say, how does this relate to the emergent behavior? So basically, this is no emergent behavior discussed at this level. We have some phases or steps to develop the system. At each phase, we recognize a set of behaviors. Each set of behaviors can be finite or infinite. So the fact that we're using a circle, that should not imply that the set of behaviors is finite. It can be infinite. And the overlapping, of course, in an ideal system, it should be one circle, or at least they should be included in each other. But from a real-world perspective, this can be the case, that those circles, they can overlap in different ways based on the development process that the developer chose to his system. But basically, those are the most relevant or the most important phases that we have when we develop the system in waterfall model or in V model or other models. So our approach was based on discussing at each phase how does the emergence phenomenon or the emergent behavior more particularly relate to the corresponding set of behaviors. So at each phase, how do we see the emergent behavior? How do we define an emergent behavior in relationship to that phase? Of course, this comes by having in mind that the emergence phenomenon already exists in different fields. As I mentioned before, in biology and other sciences, the challenge is how to find the room for the emergent behavior, or how does the phenomenon fit into this process. Where is the emergence happening exactly, the source of emergence? Yeah, so starting from the end, at least let's start with the obtained behavior, which is the behavior that we have at runtime, also called the resultant behavior, the real-time behavior, the runtime behavior, different namings in different literatures, but what we mean with it is the behavior that we obtain at runtime. One of the conclusions that we make about it is it can be observable as well as can be as non-observable. This is based on the fact that the emergent behavior can be faulty behavior, so faulty behavior is an emergent behavior. It can be observable and it can be non-observable as well. We consider the emergent behavior as a subset of the obtained behavior, which means that the emergent behavior is something that we obtain at runtime. There is no emergent behavior at design time, for example. It's something that happens at runtime. Now, if we go phase by phase, again, that was the whole approach. If we start with the intention, with the intended behavior, which reflects the intentions of the stakeholders, the clients, what are the intentions of the software system, what they want from the software system, or how the software system should function based on the stakeholders' intentions. At this level, we call this description of intentions as the intended behavior, which is the behavior that describes the set of intentions, and we think that it can overlap with the emergent behavior. It means for the stakeholder, if we have a set of components that are put together without previous planning, without a human intervention, there must be a way, or there must be a behavior that can emerge to achieve those goals. And this is why we say that the emergent behavior can overlap with the intended behavior. It means we can have the intentions that a behavior should emerge at runtime, and that the emergent behavior can be beneficial if it achieves the goals, or neutral or detrimental if it does not. Moving on to the next phase, the specified behavior, which is the result of the requirement engineering process in the development process. So the specified behavior comes after engineering and formalizing the set of intentions into a set of complete and consistent requirements and specifications. So the specified behavior can specify some requirements and properties that are fulfilled using the emergent behavior. Or at least this is what we think. We think that at this level we can specify some requirements or some properties, and we say that the emergent behavior, we do not specify how it should take place, but we can specify some requirements that needs to be achieved using the emergent behavior, which led us to think that the emergent behavior can overlap with the specified behavior. So one more conclusion is that the emergent behavior, in this case, it's not only expected, because it's commonly known in many papers that the emergent behavior is that unexpected behavior. But what we try to say here, sometimes it's expected and it can be required to take place in order to fulfill some requirements. So one good example could be the self-X properties, such as self-organization, self-adaptation, where the components achieve a system property without a previous planning or human intervention. So just to put these findings together, what we're trying to say here is that the emergent behavior, which is in a green circle, is the obtained behavior, is something that we obtain at runtime. It can overlap with the intended and specified behavior. In this case, we see it as a beneficial or good emergent behavior because it fulfills some requirements. Sometimes it does not overlap, and this is maybe the common type of emergent behaviors that's discussed in many papers. It means the emergent behavior that we did not intend or specify to take place, but it took place anyway, it emerged at runtime, and we think that this kind of behavior, it can be beneficial, it can be neutral, or it can be faulty. Or it can be a non-specified, or it might be the case that the behavior fails to emerge. In this case, we have some requirements, and we are supposed to have any behavior that emerges at runtime, but no behavior emerges. And then we move to the next phase, which is the design behavior, the design phase, and it's the key phase in our definition to the emergent behavior. So basically we have a design in the form of Petri nets, Markov chains, state machines, whatever the technique that you choose to, or the model-based approach you choose to design your system. The behaviors that this design represents, we call them the design behavior. And at this level, what we say is that the emergent behavior is something that is not designed. This is how we reasoned about the emergent behavior. The fact that you design a specific behavior and you obtain it at runtime, what you obtain is not an emergent behavior. An emergent behavior should be a behavior that is not explicitly, or it is not designed at design. It is not included in the description of the design. Yeah, so again, this is the key conclusion that helped us define the emergent behavior to be the non-designed behavior that is obtained at runtime. Nevertheless, we say that particular design descriptions lead to obtaining different emergent behaviors, because basically, depends on your design, the set of design behaviors is defined, and then what we're saying is what's left from the behaviors that can be obtained at runtime, those are the emergent behaviors. basically, we recognize two types of designs, explicit design and implicit design, but this is something we don't include in our paper. We just regard the design to be explicit design. But I just mentioned this here to make things more smooth and more understandable, that we're talking about explicit description and design of the system, and any behavior that we have at runtime that does not comply with this design is an emergent behavior. We also mentioned that the emergent behavior is a property of a single system and not just as well as a hierarchical system. It means we can have one system, we can have one single system that acts in a faulty way. We call that behavior an emergent behavior because it's not something that is included in the design and needs to be controlled and handled. In the paper, based on this informal definition, we try to make things more formal. So if we said that the emergent behavior is the non-designed behavior, then if we have a formal description of the design, it is straightforward that we can deduce what is an emergent behavior in a formal way. So basically, we give an example of a deterministic discrete event system phi that is represented with this tuple, and we say that based on this system, we can define what is a normal behavior, which is the obtained behavior that complies with the designed behavior. So the normal behavior can be described in this kind of in a list of this kind of tuples: current state, input function, input event, output event, and the target state. And of course, it's a normal behavior as long as these trace that includes those tuples, they are generated based on states that are well defined in the set of states in the design and with respect to the transition function and output function, based on which we come up to the definition of the emergent behavior. So again, the emergent behavior also can be represented in a very similar way, but what makes it emergent is the fact that we have a state, for example, that is not defined in the design model, or we are reaching a state not based on the transition function, or we are observing or witnessing an output event that is not defined, or it is defined but not with respect to the delta function, or the lambda function in this example, sorry. Yeah, so in another notation we can say that the emergent behavior is the set of behaviors that are obtained at runtime, but not the normal behaviors. So the set of all behaviors, we subtract the set of normal behaviors. So the scenario that we have chosen in the paper was about a traffic light system. We chose a widely used system just to describe it. It would be easy to see where does the emergent behavior fit, or our understanding for the emergent behavior fit. So basically, it's a system of described as a finite state machine. We have three states: green, yellow, red, and we have some input events, output events, and we have a design of how the system should function, based on which we define again a set of normal behaviors. In this example, we recognize three normal behaviors. For example, we are at state green. After 57 seconds, we have a fired output event, show yellow, and then we move to yellow. Same thing from yellow to red, and same thing from red to green, based on the time ticks and the signals to show that light. Which leads us, if we adopt our definition, the emergent behavior will be any behavior that does not respect the designed behavior, or it's not a normal behavior. So basically, if we see that output events or some new states or some new colors that are taking place, this is automatically be considered as an emergent behavior. Maybe one thing that we wanted to grab the reader's attention to is that this kind of behaviors, they might look they might look faulty, but some behaviors in some scenarios they can be beneficial, and maybe the stakeholder or the operator of the system can choose to keep it. We gave a small example. It's a naive, simple example because the challenge was how to highlight that emergent behavior can be beneficial. So, for example, if you want an emergent requirement, which is a requirement that is fulfilled using an emergent behavior, pedestrians, for example, pedestrians should not queue for long and must be able to cross as soon as the road has no vehicles. The same for vehicles should not queue for too long. These requirements cannot be fulfilled using the design of the systems, but assuming that those traffic light systems can be enhanced with a design, not to fulfill the local requirements, but it will enable them to interact. And hence, the fact that they are autonomous, it means they can make decisions, then they can interact. Some behaviors that have no previous design or previous planning can take place. Those behaviors, by our definitions, they are called the emergent behavior because there is no design to define them or explain them, and they can help fulfill some requirements, such are those requirements, or can help have some good properties to the system. And hence, this kind of emergent behavior can be beneficial, and we can decide to keep it. As a conclusion, at the end, in this paper, it was an attempt to provide a more concrete and formal definition to the emergent behavior. Our approach, of course, was based on the analysis of the software system development process, by which we could recognize that the emergent behavior can be beneficial, detrimental, and neutral. It can be predicted or not predicted. It depends. It's not only a property of hierarchical systems, it can be a property of hierarchical or system of systems, or even single systems. And what we're trying to do for future work is to adopt a formal framework process for software development and reason mathematically how does the emergent behavior relate to each development phase. So what we're trying to do at each phase, we try to define mathematically more formally, what is an intended behavior, what is required behavior, what is a designed behavior, what is an implemented behavior, and then we can reason in a better way what is an emergent behavior, and given a formal definition of the emergent behavior and those behaviors, what are the relationships? So this is basically what we're doing now, and what we mention as future work. Hopefully, we can come up with a more formal and a more concrete definition for the emergent behavior. Yeah. So that's hopefully that has been clear enough. And thank you very much for the attention, and looking forward for for the question and answers session. Explicit design.
Okay, we are live. So, are there any questions from the audience for Tufik?
Yeah. So thank you very much for listening. I believe that the topic is interesting, emergent behavior, but yeah, I welcome all the questions, the comments, the recommendations, anyone who has been on the fire of emergent behavior discussion.
Yeah, I have a question. So, your paper looks a little bit more theoretical approach. How is this taxonomy of emergent behaviors could be applied to a complex system of systems?
Yeah, definitely. The whole research started from the confusion that is out there in the literature about the taxonomy. So basically, we had different definitions from different perspectives based on different projects, and the fact that the term already existed before the project, before computer science itself, as I mentioned in the presentation in the literature, this made it difficult. So basically, we wanted to apply a definition of an emergent behavior on a project that we have in hand, DevOps, and this is where the whole research started. That we needed some more theoretical with a mathematical foundation, if possible, for the term emergent behavior.
Yes. So, and also, what else can you say about mechanisms to predict or to prevent against bad emergent behaviors? Did you think about that? How to prevent or predict bad emergent behaviors?
Yeah, definitely. So the question starts, what is an emergent behavior, which we try to answer, but for the moment, since we proceeded with the project, once you have a clear definition of an emergent behavior, it turns out to be, is it beneficial or is it detrimental? If it's detrimental, then how do you predict it? Coming to your question, how would you predict it is, you have your predefined or designed emergent behavior, and you start to check a divergence or detect a divergence from the behavior that you have mentioned in your requirements, in your design and your implementation. So the first, I would say the first divergence is the first indicator to accept the behavior as an emergent behavior that needs to be stopped, or to predict based on the observations that we have so far on the behavior that you have developed.
Good.
Mhm.
So Javier has some comment in the chat. I was probably using emergent behavior incorrectly in the past, so it will never happen again. So,
Yeah. Oh, yeah, definitely. Again,
it's a good sign as someone has learned from your work.
yeah, that's really nice. Actually, I don't say accept our definition, but at least we want to highlight that there is a big confusion about the term and the misuse of the term, and maybe we need to focus on refining the definition of an emergent behavior. But it's good to see that we're already bringing attention to the concept.
yeah, sometimes we use bad words in the papers, and we need to provide a clear definition about what we understand about a particular term to avoid the misuse.
Yeah, exactly. It sounds like a fancy term. It would be great to call a behavior an emergent behavior. This is what we sensed in many papers, but we need to be correct also, and not just.
Yeah, but it will be interesting also to provide this kind of taxonomies for different application domains, because each application domain may have different emergent behaviors.
Exactly, definitely. And this is what we recognized when we did our research.
Yeah, because we cannot cover all the emergent behaviors of all complex systems at the same time. So we need taxonomies or categorize the different behaviors for different systems.
Definitely, yeah.
Yeah, that's true. I'm not sure if there is any other comment or question from the audience. If not, there is an offline discussion room that will be open afterwards, and then we will have the closing session in a while.
Mm-hmm.
It seems there are no more questions. So
Perfect.
thank you, Tofik, for your presentation.
Thank you very much for listening.
Thank you very much. If people are interested, they can go to the offline discussion room.
Mm-hmm.
Okay. Thank you.